today is the fifth day and last day of the GAN program. So we achieved the goal during the course, and Professor uh, Zain Hum Muhammad Ahmad Ali Al-Bahi delivered a wonderful lecture. And thanks to Professor Zain to deliver the lecture, and these lectures are very much benefited for the participants and the other research scholars and students also. And these lectures they are on the Gyan portal and may be seen any time, and these lectures are very much wonderful. So again, I thanks Professor Zain Muhammad Al-Bahi. Thank you, sir, for delivering the lecture. And I would like to Professor Zain to now the session.
Thank you very much. Assalamu alaikum. Today, inshallah, we will continue our work, our lectures, our discussions in this program. Today, inshallah, we will talk about nanocatalysis. Nanocatalysis, of course, I'll try to go through some definitions and only like to remind you something. Of course, everybody knows that nanomaterials are those materials which has a dimension from 1 to 100 nanometer. This is well known. But only I would like to ask a simple question. Are nanomaterials invention or discovery? Of course, it is an invention or discovery. Your brother just said it is a discovery. Yes, I agree with you. It's a discovery. There are two types or two expressions. The presence of nanomaterial itself is a discovery. We discovered that there are some things called, not called, there are some things in this scale, yes. But nanoscience or nanotechnology is an invention. Nanotechnology, like your cell phone, these machines we are using, all of these machines are using nanotechnology. These are inventions. But nanomaterial itself is a discovery. Of course, you know these cup of glasses. These were made in 300 years AD. This means those people didn't know anything about nanotechnology or the expression of nanomaterial, but they made these beautiful glasses. And also many buildings which are churches in Europe, something like this, they have painted in nano paintings, but they didn't know also about this expression. This expression, I think, it was coined in 18th in last century only. If we classify the types or the materials in nano dimensions, of course we will have different dimensions: 0 dimension, one dimension, 2 dimensional, and 3 dimensional materials. 0 dimensions, which has no dimension outside the nano scale. All its dimensions are in nanoscale. However, one dimension has only one dimension in nanoscale, out of nanoscale, and the other 2 dimensions are in nanoscale. The 2-dimensional has 2 dimensions out of nanoscale, and 1 dimension is in nanoscale. And 3-dimensional materials, none of the dimensions is in nanoscale. So why do we call it nanomaterial if there is no dimension in nanoscale? Because it's composed of small components or particles, and all of them are colloid together or make aggregation. Like in this room, for example, the space of this room is composed of small chairs. These small chairs are in small dimension, and if we gather everything, it will form this room. Of course, zero dimension like a ball or sphere, or these, and one dimension like rod or wire. Two dimensional like something with two dimensional, like مثلا thin material, thin films or something, and three dimensional like these shapes. If we take a gold as an example, it may be formed. Gold is very unique material in the nanoscience. So it has been formed in different shapes, different sizes, from one nanomaterial to 100 nanomaterial, different shapes in spherical or rod or star, cubic or triangular, and all of these shapes are formed by gold itself. And also surface characteristics. It has different surface characteristics according to the purpose you will use. These materials are already, it is not prepared for fantasy. It is not prepared as just for science. No, nothing is made without a goal. Nothing is made for free. I mean, nothing is made without designing it to a specific purpose. We make these materials to use it in a specific purpose. So all of these materials have different functions and different decorations and different shapes. So we can use it in different purposes. We use it according to a purpose. We don't use it and look for a purpose. Nanomaterials, of course, nanomaterials, it has only two routes to be prepared. Nanomaterials has only two routes, not two methods. There are two routes to be prepared. The first route is to divide large or bulk materials to smaller pieces, and these smaller pieces is divided again to nanomaterial. This is called top-down preparation. This is a route. It is not a method, okay? Because each route has several methods. The second is if you have some atoms or some ions, some molecules, and you condensate or you try to make coagulation and precipitation or reduction for these atoms to form clusters, and then these clusters will form nanoparticles. This is from bottom up, which is from very small materials to large materials. This is another route. So we have two routes. The first one is top down, the other is bottom up. Of course, each one of these two routes has several methods of preparation. Of course, the first one, which is top down, mainly depends on the physical methods like grinding or crushing, and this is top down. Mechanical grinding or metal vapor, thermal breakdown, chemical breakdown, spontaneous chemosorption, and something like this. All of these are mainly physical methods. However, in the bottom up, it depends mainly on the chemical methods, like sol gel precipitation, electrochemistry, and electrodeposition, and the other methods. So there are two routes for the preparation, and each one has different methods of preparation. Of course, the chemistry of nanoparticles mainly depend on two factors. The first one is synthesis of nanoparticles, well controlled, and the molecular approach of more selective applications. Of course, I'd like to remind myself and you that the main advantage of using surface of getting or the main method which which we can get high surface area is to divide large particles to very small particles. This means we make division. This is the same way we prepare nanomaterials. And these are what can I say? The surface area has a great effect in all aspects or in all the purpose we use nanomaterials. Surface area. We will check this and we will look at this just now. There are some differences between bulky materials and nanomaterials. What are the differences between bulky materials and the nanomaterials? Actually, there are two properties or two types of properties. The first type of properties is the physical properties. The second type of properties is the chemical properties. Chemical properties, of course, like reactivity and catalytic activity, both of them has a great difference between the use of bulky materials and the use of nanomaterials. For bulky materials, some materials like gold, for example, doesn't work at all. It is inert. That's why we or women wear gold as like a ring or a bracelet or something like this because it doesn't react with anything. But you can't make the same thing with iron, for example, or steel because it will react sometime with some things. So gold is inert, but when it goes to nanoscale, it changes complete. Its activity changes completely. It become very active material, and we will see in next slides. For reactivity, for example, some materials has low activity in some reactions, but whenever it goes to nanoscale, its activity it changed completely as well. So both in chemical properties it change, and also in physical properties, the physical properties it changes from nanoscale or from bulk scale to nanoscale. How comes the optical? Like, do you remember this glass or cup, the couple of cups we just saw? The optical properties it changed from the angle we look at it, or from where do you put the light? Its color changes because of nano materials properties, optical properties. So and also melting point greatly change. In nanomaterials, the melting point greatly reduced. The vapor pressure, of course, changed from from nano scale to bulk scale, and also the optical material, the optical properties is changed because of the energy level spacing or quantum effect, which is plasmon resonance. I will show you what does this means. No, here, what is the effect here? I'll just mention about it. The optical properties changed. Why? Because there is an effect. If the particles, if the particles is little bit smaller and smaller and smaller, less than the wavelength of the light, this means it when it goes to another level of optical properties. This is called energy level spacing. Now, this is the main effect of changing the main effect which causes all the changes made by the reducing the particle size from bulk scale to nanoscale, which is the surface area volume ratio. Surface area volume ratio is very important. Where did it come from? It comes from, this is the particle size. Of course, the increase of particle size leads to decreasing the increase of particle size leads to increasing the bulk atoms and decrease of surface atoms. So surface atoms increases by decreasing the bulk, the particle size. Surface atoms increases surface atoms increases by decreasing the surface the particle size, and vice versa in case of bulk atoms. This is very important chart, very important relation, because it has lot of changes in the material after after preparation. Because increasing the surface area, for example, increasing the particle size, decrease surface area, and of course decrease catalytic activity, because active sites are little bit smaller than the little bit smaller than the nanoscale. Surface area and volume are both important in studying the exchange of materials in chemistry. Volume, this is, please take attention. Volume refers to the amount of space inside of the object, whereas the volume tells us how much a substance needs exchanging. In the surface area refers to the area exposed to the external environment, and surface area tells us how much of this substance can be exchanged. So the surface area tells us how much of the substance can be exchanged, because these are exposed to the external environment. Generally, surface area is a unique character. Surface area leads to increased active sites and consequently increases the catalytic activity. What about the selectivity in nanoparticles? Selectivity in nanoparticles, or the what happens in selectivity if we use the nanoparticles? The nanoparticles has different changes, like exchange in surface area, like control mix, control of crystal structure and morphology, control of surface composition, and also exposure to crystallographic facets and increased number of edges, corners, and the faces. All of these factors changes the catalytic activity, and consequently the selectivity will change or will be better. The activity of nanoparticles, as I just mentioned, related to large surface area and structure and the shape of the prepared materials. Let's go to a very important topic, which is the types of catalysis. We just mentioned in previous discussions the types of catalysis are two types: homogeneous catalysis and heterogeneous catalysis. We mentioned about it. Homogeneous catalysis means all the components, like in the reactor, like reactants and catalyst and products, are the same phase. Whereas heterogeneous catalysis, the components in the reactor, like catalyst and reactants, have different phases. These are different stories in both of them. In homogeneous, please try to concentrate a little. Inhomogeneous means like you add a piece of sugar in a cup of water. What will happen? All sugar molecules may have the ability to contact water molecules. It's very easy to contact water molecules. At this stage, so the probability of making reaction is high. At this stage, selectivity will be high. At this stage, the conversion will be high. Okay? And the probability of making reaction is very high. Okay, this is a story. The opposite story in heterogeneous catalysis. If we add just some liquid or gas and in with solid catalyst, what will happen? Only the surface of the catalyst will work. Only the surface of the catalyst will work. The bulk of the catalyst is out of scene. The molecules of the reactants can't see the bulk, so no reaction will be with the bulk. This will affect in the catalytic activity, the rate of reaction, and conversion, and selectivity, and everything. The only advantage, or the main big advantage of heterogeneous catalysis, is that you can separate the reactants or products from the catalyst, or you can separate the catalyst from the medium of the reaction. This is the main uh, advantage of heterogeneous catalysis. But on the other side, this is the biggest disadvantage in homogeneous catalysis, because you can't separate molecules of sugar out of water or something like this. This is the main disadvantage. Also, there is another disadvantage in the same disadvantage is also there in heterogeneous catalysts, but it is with little amount. Only leaching of some of this catalyst will occur in the solution and may cause some traces of the catalyst in solution. Traces, only few. And also in homogeneous, you can't separate all. Even if you use many techniques like chromatography or so, you can't separate all. Also, if you can separate all, it will cost you very much. Now, let's go to this story and see how can we treat in these problems and do it as follows. In homogeneous catalysis involves catalysis and reactants in the same phase. Okay, just homogeneous catalyst may be soluble molecules or ionic compounds, soluble or ionic compounds or something, which are completely accessible by the reactants and also soluble in the with the reactants. Of course, their structure and functional groups can easily be changed to result in chemo ratio and enantiomer selectivity, as we mentioned in previous discussion. The main disadvantage is difficult to separate from the final product or reaction mixtures that we already mentioned all about this just now. So to make separation, you can use chromatography, distillation, extraction, and all of these will not do the job 100% and also will cost you much. Okay? So the solution, they believed that the solution is to support these materials or homogeneous catalysis on a support, to immobilize these materials on a fixed support. Okay? And then we will work with these materials as heterogeneous catalysis. At this time, they found that they made a very big revolution. They made a very big achievement, that they could support these materials on a support, and then you can easily separate it. But the problem is still we have a problem of heterogeneous catalysis, which not all the catalysts will work, and also some leachings will happen and leave some traces of the catalyst in the solution. This is the solutions that they made, I just mentioned. It was entrapping immobilization of the catalyst on a support, or make attachment or reaction of this homogeneous catalyst with a support. Make a reaction to bind it together. Now, for heterogeneous catalysis, they found it has the same, it has many disadvantages as well, and the catalytic activity is low, and the catalytic activity is low, selectivity is low, and the conversion is low, and needs high temperature to occur, and something, it has many other problems. So also it has possible leaching of active catalytic sites from the solid support materials can also occur. So now we go to the solution. The solution is, they found that the solution may be in the formation of nanocatalysis. Why does the formation of nanocatalysis is the solution? Because in nanocatalysis, they could achieve the advantages of homogeneous catalysis and also the advantage of heterogeneous catalysis, and avoid the disadvantage of heterogeneous catalysis and avoid the disadvantage of homogeneous catalysis. Because when you decrease your material from very big scale to very low or in nanoscale, this means you go towards homogeneous catalysis. If you decrease, because uh, please try to imagine, in bulk materials it's very big, and in homogeneous materials, which are ions and molecules, is very small. If you take this material, which are very big, to divide, and to go to this material which are very small, this means you are going to homogeneous catalysis. You are getting the advantages of homogeneous catalysis. You didn't go to homogeneous catalysis. You just try to achieve homogeneous catalysis advantages. And on the other hand, if you are here in homogeneous catalysis and you have some disadvantages like separation of the catalyst from the solution, and you try to take these materials to bigger scale, to nanoscale, and at the scale you can separate these materials from solution. This means you are trying to achieve the advantages from each other, from both sides, and discard or try to avoid the disadvantage of each one. Let's see here that, of course, this is the story that I just mentioned, and it is here the nanocatalysis. Nanocatalysis is a very important bridge between homogeneous catalysis and heterogeneous catalysis. How comes? In the advantages of homogeneous catalysis was where high activity, high chemo and regio selectivity, means high selectivity, and less reaction time. Reaction time is quite fast, means high rate. In the same time, in nanocatalysis, we can get the same advantages, which are high activity, high selectivity, and less reaction time. Because just I mentioned that you are trying to take the material from nanoscale, from homogeneous, from ionic scale, just a little to nanoscale. Just a little. You move the size little to nanoscale. You still can have the same advantages of homogeneous catalysis. In heterogeneous catalysis, it has some advantages, which are excellent stability, easy accessibility, and easy separable. This means in nanocatalysis, it has the same advantages, which are stable and easy separable, because they are solids. You divide big solid to small solid. Still, it is a solid, but small solid. And its decrease, the decrease in its size makes it very close to the properties of the homogeneous catalysis. This is an intermediate state between homogeneous and heterogeneous catalysis. However, what are the disadvantages of homogeneous catalysis? Where the difficulty in recovery and recycling of the expensive catalyst, and this is stable, and it is not there in nanocatalysis, because we can recover the catalyst, because it is heterogeneous, and it's an advantage in heterogeneous catalysis. And the heterogeneous catalysis has this advantage, which is less catalytic activity and long reaction time. But it is not there in nanocatalysis. In nanocatalysis, reaction time is like advantages, like homogeneous catalysis. I have just remembered something I want to tell you, to let you imagine the case we are talking about, which is nanocatalysis and homogeneous, and it's between homogeneous and heterogeneous catalysis. If you compare, for example, there are three states of matter we know, and of course, besides plasma, if we compare the properties of gas, liquid, and solid, you will find that Liquid is an intermediate case or intermediate state between liquid and the solid. Okay, liquid assembles or is similar to gas in some properties, and it's similar to solid in other properties. So it acts as a gas, as a fluid in some properties like fluidity, like it takes the shape of the of the vessel and other things, and it resembles or similar to the solid in other properties like compressibility. It doesn't you can't compress the liquid, but you can compress the gas, and the other in other things. Different properties, it is similar to solid, and the other properties it's similar to the liquid, to the gas. Here in nanocatalysis, it had the advantages of homogeneous and had the advantages of heterogeneous and avoided the disadvantages here and disadvantages here. Besides, it has new advantage for nanocatalysis. What is it? It is like this. It is energy efficient, decrease the energy used. Also, it is atom economy. We just mentioned yesterday about atom economy, and atom economy is achieved in the using of nanocatalysis. Eco-friendly, efficient. Of course, people of green chemistry will like it very much. And I think this slide shows very carefully or very well how the difference between these three stages and the nanocatalysis. Now we are, I think, this is a complementary statement that it says that we can control the reaction by controlling the material we are trying to prepare. Like if we prepare nanocatalysis, we can control, you can control the size, you can control the structure, you can control the shape, you can control everything during preparation. And I think, or I am sure you know that preparation of nanocatalysis is much easier than preparation of any other materials. It is very easy. So people who are working in nanocatalysis, the field of nanocatalysis doesn't need anything except some tools to make characterization. But the preparation itself, anybody can do it just with very very simple equipments. You can prepare nanomaterials, but only you will need some tools to characterize, which you will need the same tools to characterize other properties. So characterization is a main problem in either ways. But if you go to prepare organic materials, for example, you will suffer a lot. But if you go to prepare nanomaterials, it's very simple. So, and also you can control the shape and the structure and the size. You can control. You can control everything. Everything under control. Now, there is a big question, which is nanocatalysis. Is it truth or hype? Is it truth? Yeah, it means is it a fact or just fantasy or imagination for those people who are working in catalysis that they are proud of themselves? We are working in nanocatalysis. Our science is nano science or nanocatalysis. What do you think? Is it a truth or not? Of course, they they may be right, but they may be wrong. How comes? They may be right because we explained yesterday that the reaction occurs on very tiny, very small parts of the catalyst, which is the reaction occurs in on the nano scale. But can I see it or not? Did I intend to do it or not? Did I prepare the site for this reaction or not? This means I didn't do anything of these. So I didn't intend to do it. So it is not belonging to nanoscience. Okay? But in the same time, it's actually occurring on nanoscience. Actually, it occurs on nanoscale. So they said, okay, let's make everybody satisfied. Everybody will be happy. Okay. We didn't prepare, but it occurs on nanoscale. Uh, uh, yes, they just said several researchers have catalysis is always nano, but of course, if we believe them, so we will ask them about a very big question: why does gold doesn't have, if it is in any way will happen, so why does gold doesn't have activity in bulk scale, but it has activity in nanoscale? This means it is always nano. This means it is not the same case. There is no reaction at some time. There is no reaction at some times. Then it is not working in nanoscale. But in the same time, they answer this question. Yes, it is not working in bulk, but when it goes to the nanoscale, several structure, several things, or several edges, or several energy, high energy spots or high energy sites on the surface may be acceptable or may be accessible to make the reaction. Why is gold not active in its bulk state when it exhibits extraordinary catalytic activity? It is very active. Catalytic activity when reduced to nanoscale. It is very simple. And also there is another example, which is copper oxide or cobalt oxide, which is very active in nanoscale and less active in bulk scale. Of course, we can, it's a kind of debate. Catalytic interactions are always in the nanoscale, but of course it is catalytically using something. It's okay. Now we will go to we will go to another slide, which is the effect of nanocatalysis in green science. It has many effects, and because it has many, as you can see, it makes many factors or many effects on the on catalytic activity. Number one, it's adapting magnetic nanocatalyst recovery. Number one, it because adapting magnetic nanocatalyst recovery. Actually, this item is very important because people who are working in nanocatalysis invented, this is invention, or try to make new shape of catalyst, which is the core shell, especially core shell, because they use the unique property of magnetite, for example, with the properties of other materials which will be the shell later on. Okay, and we will explain it later in this lecture, inshallah. And this is number one, which is use the magnetic properties of the nanocatalysis to enhance the recovery of the catalyst. Means if you have some magnet and you have magnetite in the solution, you simply put the magnet on the wall of the glass, and it will attract to all the material which has magnetite to the magnet. This means easily separation. And mixing ionic liquids with metal nanoparticles, this is the second. And then creating electrodes with nanocatalysts with improved redox properties. Of course, the electrodes are very important. And in the same way, the nanocatalysis is used in this way in fuel cell. We just mentioned about fuel cells yesterday. It is being there on the membrane to make the reaction of fuel and to burn hydrogen and release energy. But of course, it's very sensitive to carbon monoxide, as we mentioned as well. Encapsulating nanoparticles in nanoporous cavities like zeolites. We will discuss about zeolites today, inshallah. It has many cavities, many pores, which you can easily push and add or enter these nanomaterials inside these cavities. Of course, if you get a rod of metal, rod of iron, rod of steel, you can't put it inside the cavity of the zeolite, but you can do with the magnetic or the nanoparticles. Controlling the shape of metal and metal oxide. This is another advantage of these nanoparticles, which are you can control everything, the shape and also the size and everything. And then by controlling these factors, you can control the catalytic activity and selectivity, because selectivity and the catalytic activity are also related to the shape and also related to the size of the nanoparticles. Here we can see that the catalytic activity or the catalytic properties of nanoparticles depend on several factors, which are the size of nanoparticles, the shape of nanoparticles, composition, interparticle spacing. What does it mean? The interparticle between the materials on the surface. If the space of the between this material, the nanoparticles on the surface is large, it will give activity different from that when these materials have less interparticle spacing. The oxidation state and the support of nanoparticles. All of these materials, all of these factors affect the nano affect the activity of nanoparticles for any reaction. Let's take one by one. The size of nanoparticles. Of course, there are several experiments or several articles have been published in this topic, which is the activity is it changes by decreasing or increasing the size of the catalyst. Like this, in this case, the relation is inverse. The smaller nanoparticles, the more catalytically active, because the smaller nanoparticles, of course, means increase of surface area, means increase of accessible active sites, and increase the catalytic activity. And there is something quantum size effect. This is also, I have it just mentioned now. Other researchers, no, sorry. Research speculating originally that this behavior could be, which is this reaction due to the quantum size effect. What is the quantum size effect? It describes the phenomenon where material properties change drastically when the size of material becomes comparable to the wavelengths of the electrons or other particles within it. Other particles within it, of course, this material has different particles. The size of reduction alters the electronic, optical, and other physical properties of the material. For example, this example is already mentioned there. This is the first factor, which is the size. What about the shape of the nanoparticle? The shape of nanoparticles, there are different shapes of nanoparticles, as we mentioned in previous slides, that there is spherical or hemispherical or rods or maybe cubic, different shapes, or core shell or star, or there are or ring, different shapes. The shape is different. When the shape is different, of course, the catalytic activity is different. Like the case of the oxidation of CO by gold, nanoparticles in hemispherical nanoparticles were found to be more active than spherical ones. The hemispherical is more active than the hemispherical one. For other example, the silver nanoparticles, nanocubes, were found to be more active than nano spherical and triangular nanoparticles, as we can see in this figure in styrene oxidation. The reason for these dramatically changes are attributed to, of course, the increase or decrease in the relative area of catalytically active surface facets. or the differences in stability for different nanoparticles. This means that in the other slide, the size change makes different catalytic activity, and in here the shape change makes different catalytic activity. What about the composition of the active sites? The composition of the catalyst. If the composition changes, of course the catalytic activity changes. Like alloying of platinum with other materials, it will cause different catalytic activity. It will cause changes in the electronic properties, of course, and will change the catalytic activity. For example, alloying of platinum with rhodium or nickel or cobalt will change the catalytic activity of CO oxidation because of the poisoning of CO on these catalysts. What about the force factor, which, and this is an example data, which however, the alloying of platinum with iron, rhodium, palladium, here the there is these are two, platinum and platinum oxide. In case of platinum, in case of platinum oxide, the activity of platinum itself is higher than the alloying. And in case of platinum oxide, it is different attitude, different behavior. In general, the change in the composition of nanoparticles, it changes the electronic structure of metal surface by the formation of bimetallic bonds as well as the modification of metal bond lengths. The fourth effect is the interparticle spacing between nanoparticles. We just mentioned that the change in interparticle spaces will change the catalytic activity of the particles, like the catalytic activity of and stability of nanometer, 2 nanometer gold dispersed on the polycrystalline titanium carbide films displayed a strong dependence on the interparticle spacing. Because when it was 30 nanometer, the difference was 30 nanometer and 80 nanometer, it gave different catalytic activity. Like in this, of course, it is, I think, this data I have also just mentioned about it. Now we will go to the other factor, which is the I think it is the same idea. The oxidation state. Changing the oxidation state leads to increase or decrease the catalytic activity. It is not always the same behavior. Sometimes decreasing the catalytic activity, decreasing the oxidation state may increase the catalytic activity, and increasing the oxidation state may decrease the catalytic activity, case by case. I think these are changing the effect of platinum metal and the platinum oxide, and these are different cases about this. Now we will go to the support change. If the support change, it will also change the catalytic activity. Whereas if we use magnesium oxide as a support for gold, it will give different catalytic activity than other supports. And I think this idea has been already declared. Now we will go to other part, which is the core shell. Can we take a break for 2 minutes? About it before, but now I'll give a section for this very important materials, which are the core shell materials. And there is a question, which is why do we prepare core shell? Actually, it is the same idea if you prepare before they were using metal or metal oxide as a catalyst. After that, they thought that if we add, for example, iron oxide with cobalt oxide, iron oxide has some properties for making a reaction, and the cobalt oxide has different properties. If we mix both of them together, we will have a new catalyst which has the properties of both of them. We will take advantage of iron oxide and or magnetite, and the advantage of cobalt oxide. So we will have better activity and better selectivity, and the reaction will be better in all cases. It is the same idea that we, but the other one which were preparing was not in the nanoscale. And this is a new material which is prepared in nanoscale and has unique properties, but it has the same base that the old one is was already used. The base is it is prepared to combine the desirable properties of two materials, enhancing their overall performance and functionality in various applications. This purpose is the same old one which we were used in 18th and 16th and very old before. But let's imagine how fantastic the preparation of this core shell materials and the magnetic, especially magnetic materials. If this is a tube, as you can see, I have just mentioned that if you have a tube and this is magnetite inside, you can easily just separate by using a magnet like this, and it goes like filtration, very fast filtration, and very nice separation. This is the main idea of using the core shell, but with as magnetite in the core, because here we will see that these are the types of core shell. The core shell changes from in different composition, different shapes, and different, as we can see, different composition, which is inorganic core. The core which inside, maybe I will show you and then return back to the slide. This is the core shell. There is a core and there is a shell surrounds it. Let's return back here. The core may be inorganic, like silica, like magnetite, like titanium, and the shell may be inorganic as well, like the silica, like titanium, because you can use the same material as a core or as a shell in different cases or in different reactions. The inorganic core with organic shell, maybe magnetite with polymer, for example. Polymer, and the polymer may be prepared as a normal polymer or porous polymer. You can prepare it as well. Organic core with inorganic shell. Organic core, the same polymer we were using now, and inorganic shell like silica. Organic core with organic shell. Organic core and organic shell, both are organic. Shell, additionally, they exist various shapes like spheres, cubes, and prisms, something like that. This is a case of, again, these are not the only shapes of core shell. The left one is a core, or is a shell without a core. And of course, the left one is a core with a shell. The second one is a core, is a shell without a core. And the third one is a core but small. And number D is different cores with one shell. And number E, different shells with one core. And in this case, of course, each core will, each shell, if it is not the final one, will be a core for the next one. And these are different other different shapes. And of course, in this case, it is very nice to do it. This decoration. Of course, there is it is here. It is like this, or like this, or like this. But we added metal over this core shell to make a change in the catalytic activity and to attain different catalytic activity with different reactions. Let me show you something. And this is the core, and it is the same story that we mentioned. This is an example. We already prepared something like this. This is magnetite, and then we add titanium as a first shell, and this is magnetite with titania, and this is the TIM of these materials. It is very clear and very beautiful, because you can see here that this is the core, very clear, and this is the shell. It is the same material, but this is using TIM, but this uses HR TIM. That's why I told you before that HR, which is a high resolution TIM, is used to closely show the shape and also the arrangement of the particles and atoms. It is very clear that this is the shell and the core, and also if the shell has well arranged or disarranged or not arranged. Of course, we can see that this is magnetite, and we prepare silica over magnetite, and again add titania over the silica, and of course it can be used in conventional method, like I'll show you how conventional method, and also it can be used in plasma induced method. What's plasma induced method? We use plasma to prepare these materials. And make decoration with metal like silver or like gold or palladium, according to what you are doing to do with this material. If you are doing to do this reaction, if silver is going to be good with this reaction, you add silver. And it's a kind of promotion of these materials with these metals. Let me show you. This is how we prepared it. We added magnetite. We prepared magnetite by mixing both ferrous and ferric for some time, make co-precipitation, and we obtained magnetite as nanoparticles like this. And we added TiO as a source for silica to make a shell of silica. Then again, we added titania source to give titania shell. This means we have, how many shells we have? We have 2 shells, okay? And we make decoration with silver. We can make decoration with silver for this material by plasma or by conventionally by adding silver and reduce it over these materials. For the word reduced, I mentioned several times that the preparation of nanomaterials is much easier than preparation of any other thing. It's my opinion, okay? Because I will tell you a very simple experiment that if you bring silver nitrate solution, dilute silver nitrate solution in your laboratory and add a little bit, few milligrams from citric acid, for example, and just continuously stirring it with very dilute drops of sodium borohydride. It is not green chemistry, okay? But you add few drops of sodium borohydride. You will directly get with some heat around 60. You will directly get reduction of silver to form silver nanoparticles. The problem is how to keep it and how to investigate and characterize it. But preparation itself is much easier than you imagine. If you get this silver and put it in light, it will be reduced to nanomaterials. If you put it just under light, which is UV light, it will be reduced to nanomaterials. If you added some green materials extracted from plants or something, it will be reduced to nanomaterials. The problem is how to keep it and how to investigate it or characterize it. Adding these silver nanoparticles over these materials is much easier. And we add it in other way, which is the plasma technique. I'll show you something now. And this is the same technique, but using, instead of conventional method, which is the first line, we use plasma to prepare these materials. We prepared magnetite, and then added silica in presence of plasma. Then silica formed the first shell, and then we added titania, and titania formed the first shell. Of course, I didn't do it by myself. My student did it. Okay. The difference is, what is the difference, Professor, between doing this reaction here and doing it here? Because if I can do it with conventional method without additional technique, why do what is the benefit of using plasma if we can make it like this, and the plasma will be expensive? Because of this factor. Because of this factor. This factor is, here you can do it in 32 hours. Here you can do it in 7 hours. This is the first factor. Second is, when we measure the catalytic activity of this material and this material, it is completely different. This material has much more catalytic activity in the desired reaction. Let me show you. This is a simple setup of the plasma, where this is magnet and this is beaker. Okay, and this is 2 electrodes of plasma, and of course power. This is how it goes. Of course, we used silver as electrode. Here you can see how did we introduce the silica. This is the source of silica, TIUS, and we added dry nitrogen here, and goes to TIUS and carries TIUS with the gas to the medium which has magnetite, and continuous steering in presence of this plasma discharge here for 2 or 3 hours, and it goes to silica will form a shell, and again we make the same thing with using titania source to our material in presence of plasma to give us the total FTS material, core shell. And this is a picture, and I'll show you a video here, I think. This is the preparation of adding silica to magnetite to form silica magnetite core shell. Sorry again. I'll show you this one. This is TIUS. It has it's bubbling here to take nitrogen is bubbling to take here. You can see this is the plasma. This one electrode, and this is other electrode to make plasma discharge, and it makes the it shows forms the core, forms the shell over magnetite core. This is the first one, and the second one is the formation of the other. No, the second one is the second one is the formation of titania shell over. We added titania as a source, so we added the source of titanium isopropoxide. We added titanium source with this is 2 electrodes of to make plasma, and continuous steering until maybe 2 hours or 1 hour. It will form the it will form the double shell, which is titanium. And we took these materials and make investigation. I will show you how it goes. No. This is the 10 images of these materials, and you can see the core shell, the core inside the shell, as you can see here, and also we get some data of HR10, like here, and these are other HR10 data, and after decoration with silver, this is silver. This is black point there are silver over FST, which is magnetite. F is silica. T is titania, and decorated with silver. And of course, this is a decoration of silver. You can see it here very clearly. Of course, I will not go inside these pictures because it will be useless. Only the idea, and you can see how we could prepare it. And I think just this I will only show you. I will not explain in depth, but I will only show you something. This is ESD mapping for the prepared samples. Of course, you can see here different colors. This is another technique to identify the type of material you have. This is different color. The elemental mapping images suggest that iron, silica, titanium, and oxygen atoms were concentrated in the central zone. No, I want to say this. Existence of oxygen in red. This one, this picture means you have oxygen here. The green is silica. This picture means you have silica. Titania is yellow. This picture means you have titania. And the iron is purple, this one. And these points are for silver. I think you can clearly read this data. We didn't invent that this is oxygen, and this we also read or tried to make literature review and discovered what not discovered, just understood what other people did, and it is mentioned that these colors means these materials or these elements. By here, this is UV for this sample, and I'll show you only this one and finish. I'm sorry, I make it long today. This is the magnetic susceptibility histogram, and the black one is for Fe3O4. So this is the magnetite, the prepared magnetite. This one, after adding ST, silica, and titania, this one, you can see the difference or the height little bit shorter. It is much decreased. This means that it is chelated or something around it, something isolated from detection. This is only magnetite, and this material is this one, which the magnetic susceptibility decreased in both cases, means the magnetite has shielded with a shell in both cases. And this is the catalytic activity of our prepared samples. Of course, this is a plasma prepared sample, this one. You can see the concentration of the dye decreased, and this one is no catalyst, and this is only FST, which is the catalyst prepared by conventional method, and this is prepared by plasma method. And this work was published in this journal, which is ACHM, has impact factor 23. It's top 5 journal, alhamdulillah, this year. And now, thank you very much for your attention, and I am sorry I make it late. Thank you very much.
Thank you, Professor Zen. If you have any other query or questions, please, you can ask. Audience, is there any question? Thank you, Professor Zen, for the wonderful lecture from the very beginning. And we'd like to go uh, give thanks to Professor Zen for the first session. Then we'll get a quick break, take a tea, and just come back. Okay? Thank you.